14.7 continued. Let's look at some examples of applying the second partials test. So let's suppose f of xy is this polynomial in two variables, 1/3 x cubed plus 4/3 y cubed minus x squared minus 3x minus 4y minus 3. Find local extrema and saddle points. So we are going to apply the second partials test on this. So you got to state a couple things. So we have to say f is a polynomial, so it has continuous second partials on R2, and then we will do this calculation step by step. Okay, so let's get started on it. All right, so since f is a polynomial in two variables, f is continuous and differentiable on R. And even more, actually what it says more precisely is f has continuous second partials on R, subset of the reals. Well, actually, I should just say on R2, huh? I mean, it's the whole thing. So that's true because f is a polynomial, so just say on R2. Okay. So to apply the second partials test, basically we start taking partials. So we do partial of f with respect to x, take the second partials, so this respect to x, and then with respect to y. So with respect to x, you get x squared minus 2x minus 3. And then partial f with respect to y, you get 4y squared minus 4. Now, we're going to need this anyway, so you go ahead and do the partial respect to x again. So partial fx again, and you get 2x minus 2. And then you need partial yy, do that again, and you get 8y. And then you need a mixed partial, we're going to square it. So partial xy, and you get 0. And you can see if you did y and then x, you'd also get 0, which you know is the case. So in our second partials test in the discriminant, we see that this is going to be squared, which is just 0, and then you calculate that at your critical values. So now what we do is we look at this system and we solve that system. So we take that system, set equal to 0, and solve. So partial fx equal to 0, partial fy equal to 0, and then you solve that. Okay, so we'll just run up our system. So you have x squared, and this could be, gosh, it could be anything. Well, not anything, but you could have a lot of different possibilities when you solve this system. Sometimes it's linear, sometimes it's nonlinear, sometimes the equations are not related, sometimes they're related. Okay, so those both have to be true. So we're basically finding values of x and y that satisfies both equations. That's what you're always doing when you're solving the system. So in this case, what we notice kind of right away is that this is just an equation in terms of x, and the second one is just an equation in terms of y. So these are independent of each other, like completely. So you basically just solve each one, you get x minus 3 times x plus 1 set equal to 0. And this one you get y squared. I'm just factoring a little bit. Just divide by 4 on both sides. Minus 1 equal to 0. So we can see you get, for the top one, you get x equal to 3 and negative 1. And then the bottom one, y is equal to plus or minus 1. So since these are independent of each other, we have 4 different solutions. So I'll just try to explain that slightly, I guess. So since the equations are not dependent on each other, there are 4 critical points. So there's 4 of them. So the critical points, we have to list out all 4 of those. And so it's going to be basically 3, 1, 3, negative 1. Negative 1, 1, negative 1, negative 1. Those are 4 different possibilities. So 3, 1, 3, negative 1, negative 1, 1, and negative 1, negative 1. All right, so next we can calculate our discriminant. Our discriminant are these partials. Partial fx, fxy, fyx. So it's this determinant is what you would basically memorize or write down on a note card if you were in a regular class and you had to memorize something. That's what you write down. So partial fx, partial fyy, fxx. I say that? Yeah, okay. And then fxy, quantity squared. Okay, so you get like the function first, and then you can use it to substitute. So we're going to get that function first. So that's just going to be 2x minus 2 times 8y, and then minus 0 squared. So that's 16 x minus 1y. So we have that my d of xy is equal to 16 times x minus 1 times y. Okay, so, I mean, that's really, oops, where did that go? We're just going to put that back. I didn't mean to copy that. I was just going to move it up a little bit. So that's what we're going to use, of course, to calculate our discriminant. Or that is the discriminant. It's got to use it to calculate. So we can be very organized about this and make a table. So we can write our critical points. Then we can write the value of the discriminant, d. Then we'll write down the value of fxx, and then we'll write down our conclusion. So we'll basically make like a little chart to organize what's going on. Okay, so we'll do 3, 1, 3, negative 1, negative 1, 1, negative 1, negative 1. And we'll do we're going to calculate d 3, 1. So we are taking 3, 1, substituting in and evaluating. So you can check this. So double check, make sure these look right to you. So you get 32, which is greater than 0. And then if it's greater than 0, we calculate fxx, evaluated at 3, 1. And you get 4, which is greater than 0. So what's your conclusion? Therefore, local what? That's a local minimum. So 3, 1 is a local minimum. And we can find the values if we want. We'll do that later. Okay, and then 3, negative 1. So you calculate the discriminant. And you get negative 32, which is less than 0. Okay, so if it's less than 0, this is not applicable, and it's a saddle point. Negative 1, 1. Calculate the discriminant. And you get negative 32 again, which I find is strange when you do this, but you do. And again, that's not applicable because it's negative, and it's another saddle point. Okay, and then now calculate negative 1, negative 1. And you get 32, which is positive. Therefore, you calculate fxx. And you get negative 4, which is less than 0. So that's a local maximum. Again, just following the process. So that's how you do it. Once you get to discriminate everything, then you just follow this. So often the tough part for these type is really just solving the system accurately. And then you just follow that to figure out what's what. We could calculate like some points if you want. So you could do, f, it depends on what's asked. I mean, I assume you can just plug in these points and find the value, but so you get negative 44 thirds on that one, and then you do negative 1, negative 1. Okay, so what was 3, 1 again? 3, 1 was a minimum, so this is a local min. So you can kind of just verify, like what you're getting. So check these. I mean, I didn't just do it in my head. So it's a local min. So write down, that's your local minimum actual value. And so it's negative, that makes sense that it's that one's negative and then this one's positive, and it's calling it a max. So you kind of verify what it is. And then you can get the saddle points as well, same kind of way. And so if you're asked to put it, state the point, then you actually just put it in this form as a point. Like this. Okay. And then, okay, so negative 1, and 4 thirds. And then you can get saddle points if you want. Keep going. Let me show you the graph of that. It's right here. Okay, you can. It's kind of hard to see, and I'm just going to move it around. You can see that there's a max and a min, and then some saddle points. Sometimes this looks a little better. See that minimum right there, and then the maximum right there, and then the saddle point. Okay, so that's what it looks like. And this is the XY orientation. You can see the minimum down there, maximum there. Right, so negative was max, so that's on that side, right? See that maximum point, which is both in the negative region, and positive is down there. Then you have those saddles there and there, if you can see it. Okay, so that's your basic shape. Wireframe dots don't really do any good at all. Wireframe is there. Okay, so you can kind of see what that looks like. I'm just moving it all around so you get basically a general picture of it. What's happening there. Okay. Okay. Let's look at another question. Okay, so that was that example. Let's do one more example, and then we'll do another video for the other examples. I don't want to do like much over 25 minutes or so. All right, so this example is kind of more like an application-ish sort of thing. This one says find 3 positive numbers whose sum is 1 and the sum of the squares is minimum. Okay, and the sum of the squares is minimum. So what you do on these is you look for what is asked to be a minimum or a maximum. So the positive integer's sum is 1. Well, that's just given as information. So what are we trying to minimize or maximize? And it's this. This is it. The sum is minimum. Sum of the squares is minimum. So that's what the function we're trying to minimize or maximize. So 3 positive integers. So we're going to say assume. We'll just use x, y, and z. We could use like n, m, and w or something, but x, y, z is what we're used to, and we're going to assume that those are positive. Well, they're not integers. I don't know why I said that. They're just numbers. So we'll use x, y, z is fine. And the sum is 1. X plus y plus z is equal to 1. All right, so then we want we want the sum to be minimum, the sum of their squares to be minimum. So we want x squared plus y squared plus z squared to be minimum, like minimum values. So this if we had this as like w equals that, so if we said like, I'm going to erase this, but if I said w equals all that, then w is a function of 1, 2, 3 variables. Well, I don't want that. Our second partials test, which is back here, is a function of only 2 variables. So what will be given is other information to simplify it. And it is, of course, right here. So this is what we're given to simplify it. We have that the sum is equal to 1. So we can solve that for z. Z is usually what you would do. So z is equal to 1 minus x minus y. And then we can take this right here, and substitute right here. And now I have a function in terms of 2 variables. So that's going to be our process, is you figure out. So I actually wrote this out for us. So we want, okay, I'll say, and this is kind of information-wise, we want a function of only 2 variables. to minimize. Find a minimum of, right? So that's how we're going to substitute. So we can do that. F of xy is equal to x squared plus y squared plus, and then this is going to be squared, and I'll change my color. So it's 1 minus x minus y. Now I have a function of just two variables, and I can apply the second partials test on that. All right, so it turns out it's easier to just do the second partial and not, or do the partials and not multiply this out. And so that's just kind of like experience-wise, just do a partial. Partial fx is just 2x. That'll be minus 2 times 1 minus x minus y. And then times, well, times the negative 1, which I brought out first. So I'm going to expand this out. That's 2x minus 2. Why did I do that? I hate when it does that. 2x minus 2 plus 2x plus 2y. All right, just distributing across. So it's just 4x plus 2y minus 2 equal to 0. Okay, partial y, same idea here. So it's 2y minus 2 times 1 minus x minus y. Verify that, of course. So you get 2y minus 2 plus 2x plus 2y. All right, so you get 2x plus 4y minus 2 equal to 0. And now solve that system. So we put that into a system and solve. And so I'm going to put it in kind of a standard form. 4x plus 2y equal to 2. And 2x plus 4y equal to 2. All right, then divide out by the 2, you get 2x plus y equal to 1, and x plus 2y equal to 1. Okay, and then solve the system. All right, so we can multiply the bottom equation by negative 2 and add. Okay, so we'll go through and solve this. So we get 2x plus y equal to 1. So this is where, you could pause and try this on your own. Solving this thing is probably best. And then you add those together. You get negative 3y is equal to negative 1, so y is equal to a third. Okay, then you back substitute. You get x plus 2/3 equal to 1. So x is equal to a third. Making sense, huh? I mean, 1/3, 1/3. Guess what the other one probably is? So your critical point then is just 1/3, 1/3. This time they're related, right? Well, there's no other thing to really do, but you only get that. So these are related to each other. So once you have this and you substitute back, there's only one solution. So this is like two lines like this, and there's only one solution. Okay, so now you calculate f(xx). Well, you could have done that back there, but that's just 4. Fyy is also just 4. Fxy is equal to 2. Okay, so then you calculate the discriminant. Okay, so d of xy. Okay, and so it's just the product of those two. So you end up getting, right, it's this times this minus this squared. So it's going to be 16 minus 4. So you don't have to, show every little detail like that before. We know that's positive. You don't even have to calculate it. You just know it's positive. And fxx is 4. Okay, so that implies a local minimum, which you would basically be able to argue anyway, because there's one critical value. This only gets larger, right? So it has to be a minimum if there's only one local extrema. But the second partials test basically proves that. And then you calculate z. So refine z. So which it has to be, right? So basically you just take the 1/3, 1/3. Where'd they go? So take that and you can put it into this guy. To sum to be 1, well, it has to be a third. So z is equal to a third. And so, yeah, 1/3 plus 1/3 plus 1/3 equals to 1. And that's true. And it has to be a minimum. And the sum of the squares is minimum. So we say, and the sum of the squares is minimum. Okay, so the numbers are 1/3, 1/3, and 1/3. Okay, so that's how you can apply it with an example, and we will do a couple more next before we go on to the last section of the chapter 14.